Hello guys, welcome back to ptet.chemistry channel. So my name is Mr. On, and in this tutorial video I'll go through some specific case studies on the qualitative analysis. Actually, scrap that, not just qualitative analysis but some specific case studies into the reactions that copper 2 as well as cobalt 2, and probably if I have time some other transition metals chemistry as well, in terms of what we will see and the type of reactions that will happen when we add like concentrated hydrochloric acid, or when we add concentrated ammonia or other ligands. So I started to use this term called ligands. A-level students, 16 to 18 years old students, who have come across this term when you start doing the A-level syllabus, I guess. So you will know ligands when you come across it in the A2 transition metal chemistry, or whichever part of the curriculum that actually covers the transition metals. Okay, so this is my fume hood. We'll be using concentrated hydrochloric acid as well as concentrated ammonia. These things are corrosive because of the high concentrations, and for safety reason we have to do them in the fume hood because they fume, they produce vapor which are very toxic to you. They are corrosive as well, so you don't want it to be burning your lungs. Ideally in a fume hood, in a fume cupboard, this is a fume cupboard where I have the shares. This thing that I can, it's a thing is made of Pyrex or borosilicate, which is a kind of materials that even if something explodes or whatever inside, it will protect my eye. Ideally, I should have worn a lab coat and safety goggles. Those are standard, specific. They are very specific standard operating procedures, and that's why they are not accepted as your additional risk assessments that you need to take, because those are standard in the lab. So lab coat, safety goggles are standard. And of course, if we are dealing with corrosive stuff, we should do them in the fume hood. Anything that produces toxic fumes or corrosive fumes, or anything that can infect, anything that can affect your respiratory system, making you to have breathing difficulties, causing acute respiratory distress or something like that, you should do that in the fume hood. We should have a ventilator that will suck all the gases up there. This fume hood is a very old one, so it's in my current school, which is quite an old school. So unfortunately this thing has stopped working years ago. So but anyway, working in the fume hood is still better than not working in the fume hood. You should also have a chemical resistant glove. Chemical resistant glove mean they can withstand or they can resist the corrosive HCl aqueous or corrosive NH3 aqueous that can accidentally spill on your hand. And corrosive means they burn your skin, and they are very, very, very dangerous. Okay, I think I'm experienced enough not to use chemical resistant glove, but those are another additional risk assessment or safety procedure, safety precaution that you should take. So the risk assessment is that hydrochloric acid, concentrated ammonia, they are corrosive, and therefore you should wear a chemical resistant glove when dealing with these solutions. Okay, I'll start off by talking a little bit about copper chemistry. So this is copper metal, this is copper turnings. Copper is used in before fiber optic came along for your high-speed internet access. We use copper wire. I don't know why there's a small bottle in here. This is terrible. So that is copper turnings. There's a small bottle inside. I'll just scrape out a little bit of copper so you can see the color of copper inside a test tube. So this is the color of copper. Oh, it's not very clear, is it? I should have a white background. There you go, there's the white background. So it looks a bit, so this is copper metal. Okay, so this is the appearance of copper metal, and if you ever produce copper metal or copper solid, this is how it will look like. So a lot of books, a lot of marking schemes, a lot of exam centers, somehow they say that copper looks like a pink solid. Copper looks like a pink solid. Ideally speaking, I would probably recognize this as like a brown. It does look a bit pink depending on which angle you look at it. I think it's a perspective of light really. So I'm not too sure how well it would translate in the video once it finished processing, but that's how it looks like. So a bit of brown, pink, a bit of it's not really orangey, right? It's kind of like a bit shiny as well. Okay, so copper metal is an element. I think it's element number 29, if I'm not mistaken, in the periodic table. It's in the transition metal, so it's in the middle block there. It has got the chemical symbol Cu, and it's a metal, it's a metallic element, so it has a giant metallic structure where you have the copper cations suspended in a sea of delocalized valence electrons, and therefore you have your metallic bond between the delocalized valence electrons as well as the copper cations. Okay, so copper is also below hydrogen in the reactivity series that you have done in I don't know, IGCSE or O-level chemistry. In fact, if you are IGCSE or O-level student watching this video, you will have learned this as part of metal reactivity series. Copper is below hydrogen in the reactivity series. Copper does not react with dilute acid. Okay, if you are an A-level student watching this video, you will have realized something called standard electrode potential, also known as standard reduction potential. And you know that copper being below hydrogen in the reactivity series does not react with dilute acid, and that is a result of the reduction potential or the standard electrode potential, where standard electrode potential is taken relative to the standard hydrogen electrode, and that standard hydrogen electrode is defined to have a 0.00 volt reduction potential, and anything more positive than 0.00 would mean that it favors reductions, and copper 2+ favor reduction. So the E0, the standard reduction potential of copper 2+ and copper, if you find it in the data booklet for an A-level or IB student, you will see that they are above 0. For more reactive metals, things like potassium, sodium, magnesium, they are all more reactive than hydrogen. They are above hydrogen in the reactivity series, and as a result, they do react with dilute acid. And in terms of electrochemistry, they all have negative values of electrode potential because they favor oxidation. They like to lose their electrons. They favor the left hand side of that reduction potential as shown in your data booklet under electrochemistry. Remember that just because copper metal is below hydrogen in the reactivity series, it does not react with dilute acid at 1.00 mole per dn cube, and that's the standard conditions for a standard electrode potential. However, when we change the concentration of the acid to become a lot more concentrated, there is no telling whether the copper will react or not, because changes in concentration can affect or can change electrode potential. And as you will know, this is actually the basis of Nernst equation, N-E-R-N-S-T, I think. Nernst equation is actually part of a new syllabus in the A-level chemistry, and it was already in when I taught it a couple of years ago, so it will have been around for a couple of years. If you have done a couple of full paper tutorials, or if you go through the created topical playlist on A2 electrochemistry, you will know that you can get non-standard electrode potentials under non-standard conditions, and you can make copper react with concentrated nitric acid. So copper metal reacts with concentrated nitric acid. There is quite an important case study. You will have seen it somewhere along the line when you were doing O-level or IGCSE, because the balance equation is actually quite tricky, but the reaction is spectacular because it does not give you the usual metal plus acid giving you hydrogen. No, it doesn't. Instead, with concentrated nitric acid, copper metal will give you NO2 gas. NO2 gas is nitrogen dioxide and is brown in color. Okay, so I do have a bit of nitric acid here. I need to be careful as I'm not wearing a glove. There's hydrochloric. There's sodium. I can't seem to find what I want, but let me just grab a beaker. So I do have nitric acid in here. this one there, it shows it's nitric acid. Oh no, okay, never mind. You just have to take my word for it. There is nitric acid, I guess. So I started filming a little bit already, and I should clean out my mess. Okay, so I have my array of test tubes. Put back my nitric acid where it's supposed to be. And this is my copper metal. Let me see, is that clear or not? Give me a minute. Okay. So I'll add some nitric acid, concentrated nitric acid to this. And I hope you'll see that there's a bit of brown gas given off. I should lower the fume hood. So the brown gas is NO2 being given off. Okay, and the green solution is a result of a transition metal chemistry involving copper 2+ and some other things in the solution. Okay, so NO2 is a respiratory distress. I really need to go and turn on the other ventilator. So NO2 is a brown gas, and I really must leave this now because this fume hood has not got a working ventilator, and this gas is really bad for people who have asthma. And well, as you can see, it's a brown gas. It's definitely not a hydrogen gas, which is a colorless gas. There's a reaction between a concentrated acid and copper metal, even though copper is below hydrogen reactivity series, because concentrated acid is no longer under standard conditions. Okay, so I'll zoom out this thing. I'll leave this room for a bit, and when I return, we'll do a little bit more of other copper chemistry. So I've killed off this reaction by adding a lot of distilled water to the reaction, and the reaction has stopped. Now we get a blue solution because that is the copper 2+ aqueous. As we know, the color of copper 2+ in solutions, they form this aqua complex which is blue in solution. The reaction has stopped. The copper metal, the pink brown solid, has disappeared because they have completely reacted with the concentrated nitric acid. Okay, so I leave it there. The smell of NO2 still lingers around. It's really a toxic gas, so I should really clean this up and move away and come back to this later on. Hello guys, so back with me on this copper 2 chemistry that I'll just do an array of tests and show you some of the ligand substitution reactions that is typically part of the copper 2 case studies, and afterwards I'll do the cobalt 2 case studies. This forms the majority of that A-level syllabus on transition metals. So let's get started. So you might or might not have very good audio quality on this, but hopefully I hope that you get a decent, good enough video quality on the color changes. So I've got an ammonia solution. This is concentrated ammonia. The show is ammonium hydroxide. So not too sure if it's too clear or not. Ammonium hydroxide because you have ammonia dissolved in water. Ammonia is a gas at room temperature and pressure. When you dissolve it in water, you're going to get ammonia plus water, giving you ammonium hydroxide. So it's a base. It's a weak base because it reversibly ionizes or partially dissociates into the hydroxide ion. So what happened is we just have a very concentrated, is 35% ammonia. So despite its high solubility in water, it does fume off to give you this really pungent gas, which is ammonia gas. So I don't need a lot of it. It is a corrosive solution, obviously, so I should have used a nitrile glove, which is a chemical resistant glove. So that is not a good idea. Oh gosh, okay. The fume hood is really so what happened is the fume hood has got the ventilator not working. So in a proper fume hood, oh gosh, the smell of ammonia is really overpowering, overbearing. And if you ever smell ammonia, think of this as like 20 times more concentrated, I guess. But yeah, I'll try and get this done as soon as possible so that I wouldn't really have to bear with the smell that long. In reality, what you have is you will be given it in a small bottle, where in a small container, where it will contain the ammonia instead of it vaporizing really quickly. But I don't have that in a bottle here, in a small bottle container. So let me just get started. So the first thing I'll do is I will dissolve some copper 2. I'll dissolve some copper 2 sulfate. This is copper 2 sulfate hydrated. Blue colored crystals, whereas the copper sulfate anhydrous, it's kind of whitish because the water crystallization has been driven off. It really does not matter that much because we're going to dissolve it in water, whether we use copper 2 sulfate anhydrous or copper 2 sulfate hydrated. It does not matter at all. Okay, I'm back. I forgot the best way to do this in the absence of this properly working ventilator is to just wear a mask to prevent me from smelling too much of this ammonia. So like I said, we could use the hydrated or the anhydrous. It shouldn't matter that much because we're just going to dissolve it in distilled water anyway. Okay, so it's a water crystallization kind of compound, so it's got water crystallization. You could have heated it. You could have heated it and you would have driven off the water crystallization as a colorless liquid forming on the upper part of the tube. So this is being a hydrated crystal is quite hard to dissolve. So I'll show you if I actually have the copper 2 sulfate anhydrous. This will be the slightly easier one to dissolve in water. That will give you the exact same result. So essentially after you heat the hydrated copper 2 sulfate in water, hydrated copper 2 sulfate, if you heat it until dryness, you're supposed to get this kind of color, which is a bit whitish. And this should be a lot easier to dissolve in water. And not really, no. It is still pretty hard to dissolve in water. Should probably heat it a little bit to make it easier to dissolve. Oh yeah, this one is fine. So you can see that most of them kind of dissolve in solution already. So this is a pale blue solution. What I'm going to do is I will split it into a couple of portions. The first of which I can test with sodium hydroxide. I could test with aqueous ammonia. And then I could also test with the addition of chloride. Okay, so do I have sodium hydroxide in here? Actually, I've done the sodium hydroxide previously. I'll just append the video from the other experiments into this one. So I'll skip the sodium hydroxide bit. I'll go straight to concentrated hydrochloric acid. So this is concentrated hydrochloric acid. So I will just add onto the pale blue colored solution. I don't want to be testing the concentrated hydrochloric acid out, and that is kind of disgusting, so that is not good. I don't want to use that. Perhaps I can use this. Okay, so this is also concentrated hydrochloric acid. So let's see what happened. Let's choose this one. Not too sure if it's clear or not. I should grab a test tube holder actually. So that I won't be holding it in my hand. Okay, so I have a test tube holder. Oh no, I think it was this one that I was supposed to add. So how it is clear, this blue solution, I add concentrated hydrochloric acid to it. And it's not showing me anything. I think this hydrochloric acid is not that great anymore. So I don't think this hydrochloric acid is still that good. I will just pour out another beaker of the corn hydrochloric acid, because hydrochloric acid does actually give off the HCl fumes pretty rapidly. So if they have been stored in the cabinet for a long time, so they're not going to be very concentrated anymore. So I don't need a lot, I just need a little bit. And that is empty as well. That's empty. So it's sulfuric. This one is hydrochloric. So this one is hydrochloric acid. What I'll do is I'll just take a shopping pipette. Remember this one just now? Blue solution. I add hydrochloric acid to it. And it's supposed to change color a little bit. So this is the original blue color and it's slightly gone a bit greeny. Okay? I should keep on adding hydrochloric acid to it, and it will become clearer. Okay, so I hope it is kind of clear that it is going green. Alright, so this is green solution. This was the blue solution. The blue solution is just copper 2+ with water around it. So this is the aqua complex with 6H2O around the Cu2+. The Cl- has replaced the H2O molecule. There's a change of geometry. Now this is a CuCl4 with a 2- charge because it's still Cu2+, but it's got 4 Cl- in a tetrahedral shape, tetrahedral geometry. So it's Cu2+ and 4 Cl-, so it's going to give you CuCl4 2-. Okay, so that's green in solution. That is using concentrated hydrochloric acid. So just using normal dilute hydrochloric acid is probably not concentrated enough to drive the solution, as you could see from my earlier experiments. Okay, so that's with chloride. I should add a little bit of ammonia. So usually we will try by adding some dilute ammonia first, but instead of diluting my solution, I'll just add a bit of concentrated ammonia, and that should work. And it's oh gosh, okay. So that is the really deep blue solution that you get in the presence of excess ammonia. And I already have a lot too much ammonia actually, so that's why like I get the deep purple straight away. by right I should have a pale blue precipitate first. Okay, I think my ammonia is too concentrated. I think I'll just show you what happened when I add just one tiny drop into it. So you'll be given dilute, right? You'll be given dilute. Not really, no. You'll be given a dilute ammonia for QA. So this is essentially the initial precipitate that you will get, because the ammonia is acting as a weak base. It gives you the hydroxide ion that will precipitate out the copper 2 plus as copper 2 hydroxide, pale blue precipitate to begin with. And then in excess ammonia, it doesn't need to be concentrated ammonia, the dilute ammonia that you have will bring the pale blue precipitate to this deep blue solution. So this other pale blue precipitate, copper 2 hydroxide, is just the ammonia acting as a base, but then ammonia can also act as a ligand, and they will eventually replace the water molecule, and then you get copper 2 plus with 4 NH3 and also 2 H2O remain. It's still a 2 plus charge complex, and this is a deep blue or dark blue solution. Very distinctive color to indicate the presence of the copper 2 plus. So what happened with this complex is that it's got 4 ammonia and 2 H2O molecule with a 2 plus charge. I could drive it towards this green color solution that is copper with 4 chloride around it. So what I'll show you now is just by adding hydrochloric acid, concentrated hydrochloric acid to this. This will be my source of chloride. So this is the blue color solution. So I'm adding concentrated HCl. Oops. I think I'm accidentally pouring some of this outside. So I need to be careful. I think I probably had too much of it in there. That is not going to go anywhere at all. Okay, so slowly you could see that the solution has gone, the deep blue solution has gone green. Initially it took a bit of time for it to start because the HCl is the acid. The acid will try and remove the NH3 as the base because it's a neutralization reaction. So the HCl will react with the NH3 in the neutralization reaction to begin with. But after some time, when I add more and more concentrated hydrochloric acid, the Cl minus, what it does is it will replace the NH3 molecule as a ligand. So it's a ligand substitution reaction and results in this green color solution, which is essentially copper 2 plus surrounded by 4 Cl minus ligand. Okay, so this is just an example of a ligand substitution reaction, and it's all reversible. So I'm using concentrated style, that's why there are fumes all over. By right, it should have a ventilator that's working, so it should all suck the gas properly. So what happened to this reversible reaction is this is the green colored thing. If I add more water to it, water can compete as a ligand, and as you could see, it's a very pale blue solution now because it's gone back to the copper 2 plus surrounded by 6 H2O molecule. Okay, just like this one was in the ammonia. Oops, hang on. I need to be picking this up properly. So this was in ammonia a little bit just now. So I'm going to add a bit more ammonia to get the dark blue complex. Okay, so that is nice and happy. Dark blue complex, but then I'm going to add a lot more water. And in a very large amount of water, if I remove some of these. If I remove some of that solution and then keep on adding water, this solution will eventually, because I'm introducing more and more H2O to it, the deep blue solution will go back to the pale blue solution because it drives back the equilibrium where the water molecule replaces the NH3 molecule, and I should get the pale blue solution. So it's still pretty concentrated with the ammonia complex. So it should pretty much go back to this color later on. Okay, I'll see if I can actually put a lot more water and see if I can get it. Yeah, it kind of goes really pale blue solution now. Okay, so that's it for copper 2 plus chemistry. We'll probably stop here for the time being because it's not very comfortable with the mask and all these dangerous toxic fumes, especially with in this non-ventilator fume hood. Okay, so just to further drive home the message that we can get these compounds called copper 2 chloride dihydrate. So this is copper 2 chloride. It's kind of like blue greenish in color, but I'll just show you what happened when you dissolve it in solution. So you should get a clean spatula. Yep, that's reasonably clean. So this is copper 2 chloride. Copper 2 chloride. Okay. Oof. A bit disgusting there. It's kind of like greeny bluish in solution. And once it is in solution, you have a lot of the blue, pale blue solution instead of the greeny color solution that we saw earlier, because in the presence of distilled water, deionized water, I've just introduced a lot of water molecules, and these water molecules just basically surround the copper 2 plus. To get back the green color species, what you do is you can add concentrated hydrochloric acid to this. They will compete with the H2O molecules, and they will replace the H2O molecules to give you back the tetrahedral complex, which is the Cu2 plus and 4Cl minus. They will be greenish in color. Okay, so as a solid, this copper 2 chloride dihydrate. The dihydrate is a water crystallization, so it's copper 2 chloride, so it looks a bit greenish. As you could see, it's a bit greenish there because in a small amount of water, if I have, okay, now I can see where it comes from already. I'll just add a very small amount of water and see what the color is. How you can see the color? So this is the same compound. In the very small amount of water, it is green. Okay, just like when we added concentrated hydrochloric acid to the pale blue solution containing the copper 2 plus with a lot of H2O just now. But if I dissolve this in a lot of water, so if I add a lot more water to this is CuCl42 minus. If I add a lot more water to this is the idea of reversible equilibrium. These are all to do with ligand substitution. A lot more H2O molecules means they compete. In fact, they oversaturate the Cl minus ligands, so they will win over it, and therefore you compete with that equilibrium. You shift to the other side of the equilibrium. With the increase in water concentration, you get this copper 2 plus with 6H2O around the copper 2 plus, giving you this pale blue solution of copper 2 hexaaqua complex. Alright, so that's it for copper 2 chemistry.